Dear audience, more applications on communication system design involving thermal noise. Here is the target. This is the target, which is an aircraft that has a radar, a cross section of 5 meters squared. This is the equivalent area of a reflector that gives the same backscattering towards the radar. The radar antenna has a gain of 30 dB. The transmitter power of the radar is 200 kilowatt, and the equivalent noise temperature of the antenna, of the radiation resistance of the antenna, is 200 degrees Kelvin. And the mixer here, the mixer has a noise figure of 3 dB and a conversion loss of 10 dB. The intermediate frequency amplifier has a noise figure of 6 dB, and the required or expected signal to noise ratio of this design, of this communication system design, is 10 dB. So the output signal to noise ratio should be 10 dB. The frequency of operation is 10 gigahertz, and the wavelength is here. The wavelength is equal to the speed of light 3 times 10 to 10 centimeter per second. The speed of light is 3 times 10 to 8 meter per second, or 3 times 10 to 10 centimeter per second, divided by 10 gigahertz, 10 to 10. This here, 10 to 10, cancels with this 10 to 10, and we end up with 3 centimeters. This is 3 centimeter. The wavelength is 3 centimeter. The pulse length of the radar is 1 microsecond. So the bandwidth is 1 over the pulse length. 1 over micro is 1 megahertz. This is the bandwidth of the radar. Delta F is 1. Now we want to find the maximum range of an aircraft to obtain here a signal to noise ratio of 10 dB. If the range is greater than this maximum range, the signal to noise ratio will be less than 10 dB. If it is less than the maximum range, this ratio would be greater than 10 dB. So we want to find the maximum range distance. We find, or we calculate, the system noise temperature equivalent here at this point, at the equivalent at this point, at the antenna terminals, or at the mixer input. At the antenna terminals, we have T antenna, of course. We have T antenna, because T antenna is defined at the antenna terminals. Also, at the input of the mixer equivalent noise is F mixer minus 1 times T naught. This is the equivalent noise temperature at the input of the mixer. The IF amplifier has an equivalent noise temperature of FIF minus 1 times T naught. This would be at the input of the mixer here, and we multiply by LC because we are going in the reverse direction. We multiply by LC to obtain the noise temperature of IF amplifier at the antenna terminals. All quantities should be added at the same point. This is the equivalent noise temperature of the IF amplifier at the antenna terminals. The mixer noise figure is 3 dB, and we know that 3 dB is 2. 3 dB corresponds to 2, a ratio of 2. We can show here. It is 0.2, 10 to the power 0.2 is 3 dB. 3 over 10 is 0.3, 10 to the power 0.3 is 2 here, 1.995, it is 2. So we put here 2. So FM here, we put FM here 2. Okay, and 1 is at this. T naught is the room temperature in Kelvin, which is 290 degrees Kelvin. And antenna temperature is given T antenna here, it is 200. So T antenna is 200. If IF, the noise figure of the IF amplifier is 10. 10 corresponds to a ratio of 10. IF amplifier. Oh, it's 6, sorry. If IF of the amplifier here is 6 dB. So 6 dB over 10 is 0.6. 0.6, 10 to the power 0.6 is 4, is around 4. So we put here 4. And T naught is 290. LC, the conversion loss of the mixer, is 10, which corresponds to 10, a ratio of 10 also. Now we calculate this 290. 1 times 290 is 290 plus 200 plus 3 times 10 is 30 times 290. This is equal to 9190 here. 9190. This is the answer. So this is the system noise temperature, the equivalent system noise temperature referred to the antenna terminals. Now we calculate the noise power. The noise power is, we multiply TS by K delta F. We return K delta F. K is the Boltzmann constant, 1.38 10 to minus 23, and the noise temperature is taken from here, 9190, and the bandwidth is 1 megahertz. 1 mega is 10 to 6. Here 10 to 6. So when we multiply this, it is 1.38 10 to minus 23 times 9190 times 10 to 6 equal to this value, 1.27 times 10 to minus 13. If we multiply by 10 to 13, we obtain 1.27. So it's 1.27 10 to minus 13 watts. This is the noise power. Now from radar equation, we have P received equal P input or P transmitter, wavelength squared, radar cross section of the target, gain of the antenna squared, and 4 pi cubed, and range to the power 4. Now this is equal to, P input lambda naught is 3 centimeter, so it is 0.03 meter squared, and the radar cross section was 5 meter squared, and the gain here you can see radar cross section is 5, and the gain is 30 dB over 10 will be 3. 10 to the power 3 is 1000. It is 1000 squared. 4 pi cubed, and the range is unknown. This is the unknown parameter here. This is unknown. This quantity Okay, take here. This quantity is unknown. Now, since the signal to noise ratio is equal to 10, this means that the signal is 10 times the noise power. The noise power, we have already calculated the noise power. It is 1.27 10 to minus 13. This means that the signal level is equal 1.27 10 to minus 13 times 10. It will be equal 1.27 10 to minus 12. Here it is. It is 1.27 10 to minus 12. This is P received. Now, this equal to this, and the only unknown in this equation is P input. Is P received. This is P received is known, and P transmitter is known. It's 200 kilowatt. So here P input is known, and those are constants. This is unknown, and P here is known. So the only unknown here is R. The answer is on this page here. So we take R to 4. It is equal to 24.4 kilometer, which is equal 15.2 miles. 24.4. This is R to 4. Let's calculate it. Is equal to, we take R to 4 to here, and here we interchange this with this. So we put here R to 4, and we put here 1.27 10 to minus 12. Now we calculate. P input is 200 kilowatt. Is 2 times 10 to 5 times 0.03 squared, 0.03 squared times 5 times 1 million 10 to 6 divided by 4 pi cubed times pi cross cubed divided by 1.27 10 to minus 12. Equal this is you can see here it is 357 and we have 10 to 16. If we multiply by 10 to minus 16 here this times 1 10 to minus 16, it's equal 35.7. Here it's 35.7. If you take this is to the power 1 over 4, you will get this value. Okay. Now let's consider, we will consider another example here. An incident wave on an antenna here. The gain is 30 dB and the antenna temperature is 20 Kelvin. The transmission line loss is 3 dB. The ambient temperature 290 Kelvin, and the mixer loss is 3 dB. Noise figure is 4 dB, and the IF amplifier noise figure is 6 dB, and signal to noise ratio is 10 dB, and the bandwidth is 1 megahertz. The wavelength is 3 centimeter, and we want to find the system noise temperature. We calculate the system noise temperature here at the antenna terminals. Here, calculate. So here we put T antenna. T antenna is 20 Kelvin. We put here 20 Kelvin. This is 20 Kelvin. And for the transmission line, we calculate it here at its input. It's L minus 1 times T naught. L is here 3. 3 corresponds to 2 dB because it is 3 over 10 is 0.3 to the power 10 to the power x is 2. Here 2. And T naught is 290. This term is here. L is 2 as the ratio of 2. And the mixer for here the mixer noise figure Fm minus 1 T naught, and we multiply by L because we are going in the reverse direction. We multiply by L. L is 2 because we said that L is 2, so we multiply by 2 here. And 4 dB is 10 to the power 0.4. 0.4 10 to the power, it is 2.5 as you can see. So here it is 2.5. If is 6 dB. 6 dB, 3 dB is 2, so 6 dB is 4. And T naught is 290. The conversion loss of the mixer 3 dB is 2, is a ratio of 2. And the loss of the amplifier also 3 dB is a ratio of 2. We now calculate. Find the value. System noise temperature. Okay, if it is 20 plus 290 plus 1.5 times 2 is 3 times 290 plus 3 times 4 is 12 times 290. The answer is 4660. 4660, exactly the same answer. Now the noise power is, we take TS here and we multiply it by K delta F to obtain the noise power. K is the Boltzmann constant 1.38 10 to minus 23 and TS is 4660, and the bandwidth is given in the question. It is 1 megahertz 10 to 6. The bandwidth is 10 to 6. Multiplying this, one 1.384660 times 1 10 to 6 times 1.38 10 to minus 23. The answer is 6.43 10 to minus 14. Let's multiply by 10 to 14 and it is 6.43. Yeah, 6.43 10 to minus 14 watt. P received is equal to signal to noise ratio times P noise. Noise will cancel with noise and we will get the signal. Signal to noise ratio, it is 10 here, 10 dB. 10 dB is 10 ratio, is a ratio of 10 also. So signal to noise ratio is 10. Okay. And P noise is 6.43 10 to minus 14. This is P noise. Same value, we take this here. The answer is 6.43. 10 times 10 to minus 14 is 10 to minus 13. This is in watt. Now the received power is equal to the incident power density, radiation power density, times the effective area of the effective aperture of the receiver antenna. Effective aperture is lambda squared over 4 pi times the gain. This is the effective aperture times P incident is the radiation power density. This is unknown. We want to find P incident here in the question. We want to find P incident. So P incident is equal, this value 6.43 to minus 13 here, and 4 pi will be in the numerator and lambda squared G will be in the denominator. Now this is constant, lambda is 3 centimeter we said, and the gain was, the antenna gain was 30 dB. 30 dB over 10 is 3, 10 to 3 is 1000. What is, we put here 1000. Now to calculate the answer, find the answer, 6.43 10 to minus 13 times 4 times pi divided by 0.03 squared, 0.03 squared divided by 10 to 3, 1000. The answer is this 8.977, 10 to minus 12 watt per meter square. This is the radiation power density. This is the same, but we want to calculate here sigma, the same. Another problem here, this is also a radar problem. We want to find the range. I think, oh no, it's different. Okay, this is we want to find the range. The radar cross section is 2 meters squared. The gain of the antenna is 40 dB, which is 10 to 4, and the transmitter power is 100,000 watt. Signal to noise ratio required is 12 dB, and the system temperature, the system noise temperature, equivalent system noise temperature is 1000 degrees Kelvin, and the bandwidth is 2 megahertz. The wavelength is 10 centimeter. So the noise, we simply put 1000 system noise temperature times K delta F, and it is referred to the antenna output here. This is the antenna output or antenna terminals, because the wave is coming in this direction. So K Boltzmann constant 1.38 × 10⁻23, TS is 1000 given here, and the bandwidth is 2 megahertz, 2 times 10 to 6, and this is simply 2 times 1.38 is 2.76, and this is 6 plus 3 exponent of 3 is 9, 9 minus 23 is minus 14 watt. So this is no need for calculator. Now P received is equal signal to noise ratio times the noise. Noise will cancel the noise and we will get the signal. Signal to noise ratio is 12 dB. So let's calculate 1.2 to the power 10 is equal 15.84. This is the signal to noise ratio, 15.84. So it is around 16 times P noise is this value here, 2.676 × -14, and we will get this 4.4 × -13. Now P received from the radar equation is P input, P transmitter, wavelength squared, the radar cross section, and the gain squared of the antenna, and here the range to the power 4. Now P received is known, here it is known, P received, and the P input was 100,000 watt, the wavelength was 10 centimeter, and the radar cross section was 2 meters squared. The gain of the antenna was 10 to 4, it was 40 dB, 10 to 4, and this is 4 pi cubed here. Now if we interchange this and this, see, if we put here the P received 4.4 × -13, we will get on the other side R to 4. So R to 4 is 2.285 10 to 20, and if we take the to the power 1 over 4, we will get R, which is 123 kilometer or 76.8 miles, statute miles. An example here, we have two microwave links, or we have a microwave link, two towers. They are 50 kilometers apart, and the gain of the antenna is 40 dB. The signal to noise ratio is 40 dB also. The system noise temperature is 1000 Kelvin, and the frequency bandwidth is 10 to 8 Hertz or 100 megahertz, and the wavelength is 3 centimeters. Now the noise power is equal, we would take TS and multiply it by K delta F. K 1.38 10 to minus 23, TS is 1000 and delta F is 10 to 8, and we will get here 1.38, 8 plus 3 is 11, 11 minus 23 is minus 12 watt. Now the receive power, the signal to noise times the noise. Noise will cancel the noise and we will get the receive power. The noise, signal to noise is 40 dB, which is 10 to 4. And P noise is this value here. We take this value and put it here. And this will be 1.38 times minus 12 plus 4 is minus 8. This 1.38 into minus 8 watt. Now P received from the radar equation, P transmitted wavelength over 4 pi r all squared times, this not radar equation, sorry. This is the Fry's transmission formula. P transmitter times lambda naught over 4 pi r squared. This is the free space loss. And this is the gain squared because the transmitter antenna gain is equal to the receiver antenna gain. Now we want to find the transmitter power. So P transmitter is equal P received. Now we invert this, so this will be in the numerator 4 pi r and this will be in the denominator lambda naught, and this also will go down into the denominator. P received, we have already calculated that it's 1.38 into minus, P received is 1.38 into minus 8 here, and 4 pi r is 50 kilometer, so it is 50,000 meters, and lambda naught, the wavelength, is 3 centimeters, so it is 0.03. The gain, as we said, it is 10 to 4, 40 dB squared, and we get 6.05 10 to minus 2 watts, which is 60.5 milliwatt. The last example, we have a radar, a police, traffic police radar, and this is the target. It is a car. The radar cross section of the car is 0.2 meter squared. The diameter of the parabolic antenna is 20 centimeter, small parabolic antenna. The input power is 100 milliwatt, and the aperture efficiency is 0.6. The signal to noise ratio is 10 dB. The frequency is 10.55 gigahertz, and the system temperature is 1000 Kelvin. The frequency bandwidth is 1 kilohertz, and the signal to noise ratio is 10 dB, as we mentioned here. The gain of the dish antenna is equal to the actual area pi a squared. A is the radius of the antenna of the dish, and this is as you know that the effective aperture of the antenna is equal lambda squared over 4 pi times the gain. Okay, so the gain from this, the gain is equal to 4 pi times the area, 4 pi times the effective area, equivalent area, okay, divided by lambda squared, or lambda naught squared, divided by lambda squared. This is here 4 pi over lambda squared, and the effective area is the actual area pi a squared times the aperture efficiency, which is 8 here. So aperture efficiency is 0.6, and 4 pi times pi, it will be 4 pi squared. The diameter is 20 centimeter. This means that the radius is 10 centimeter, 0.01. It is 20 centimeter and 10 centimeter. 10 centimeter is 0.1. 0.1 squared is 0.01. And we have here also the wavelength corresponding to 10.55 gigahertz is 2.84 10 to minus 2. This is in meter squared, and we obtain 2.93 10 to 2. This is the gain of the antenna gain. Now we want to find the range. we find the noise power. It is KT TS delta F. TS is given. The system temperature, it's 1000, and this is the Boltzmann constant times the system noise temperature times the bandwidth, which is 1 kilohertz. Bandwidth is 1 kilohertz, and we obtain the noise power. It's 1.38 × 10⁻17 watt. Now P received using the radar equation is P input times the wavelength squared times the radar cross section times the gain squared over 4 pi cubed, the range to the power 4. And we want to find the range here, the maximum range, to detect the car for this signal to noise ratio. Now the P received is equal P noise times signal to noise ratio, and P noise is 1.38 × 10⁻17, and signal to noise ratio is 10. It was 10 here, so we multiply by 10, and here it will be, instead of 10 to minus 17, to minus 16. Now this is known here, and this equation here, everything is known except the R to 4. We interchange now R to 4 with this. So R to 4 is equal, here we put here P input times lambda squared sigma G squared over 4 pi cubed, and we put here 1.38 × minus 16, and we substitute the values. P input is equal to 100 milliwatt, which is 0.1 watt. As you can see, P input is 0.1 watt, and the wavelength is 2.84 × minus 2 squared. The wavelength, here it is, and the sigma is 0.2 meter squared. The radar section is 0.2, and the gain of the antenna, we already calculated that here, 2.93 10 to 2, here it is, and we have also 4 pi cubed, and P received is here 1.38 × minus 16. So we obtain here 5.06 10 to 12, and this is R to 4, of course, and this is R, sorry, this is R. After you raise this to the power 1 over 4, you will get 1.5 kilometer or 0.94 mile. So the car will be detected if it is 1.5 kilometer away from the traffic police radar, or at a closer distance as compared to that. Thank you for listening.